Okay, so it's already 4:05, so let's start. I'm Bhargav. I'm a PhD student in IISc, and for this course, I'm taking problem solving sessions every Saturday from 4 to 5. So let me present my screen and we can start for this week. So if anyone of you have any questions, just feel free to interrupt me. Just unmute yourself and ask the question. That would be preferable to putting it in the chat, because when I'm presenting my screen, I can't see the chat. Okay. Yeah. So can you see my screen?
Yes.
Yeah. Okay. So first, before we start with problems, let's quickly recall what we would have seen in this week. So the first thing that we saw was the Cook-Levin theorem. So can anyone tell me what this theorem is? Hello. Okay, so what this theorem says is that the language 3 set is NP complete. Okay, and so after this you would have also seen some NP complete problems, like for example you would have seen that clique is NP complete, the problem of independent set is NP complete, the problem of finding Hamiltonian path is NP complete, the set curve problem is NP complete, and so on. Okay, and you would have also seen the complexity class co-NP. So co-NP is the class of all languages L, so that the complement of L is in NP. So for example, clique is NP complete, so it is in NP. So the language clique complement would be in co-NP. Is this fine? It would be really helpful if you can say yes or no, because I can't see your faces.
So, sir, you are audible and visible, but
Yeah.
unfortunately, since I didn't it's all going above my head. So,
Okay.
I think maybe Vivek Kumar can say if.
Okay. Yeah. So yeah. So this is one definition of the class co-NP. There is also an alternate definition, which is the following. So co-NP is a class of all languages L, such that there exists a polynomial function P and a polynomial time deterministic Turing machine M satisfying X is in L if and only if for all certificates Y, M of X comma Y is 1. And it's not too difficult to see that this definition and this definition are the same. I think this would have been covered in the lectures for this week. So after this you would have also seen the complexity classes sigma k and pi k. So let's quickly recall their definitions. So sigma k is the class of all languages such that there exists a polynomial time function P and a polynomial time deterministic Turing machine M such that X is in L if and only if there exists y1 for all y2 there exists y3 and so on up till qk yk such that M of X y1 to yk is equal to 1. So over here let me start the laser pointer. Yeah, so for over here this quantifier qk is there exists or for all depending on whether k is odd or even, and the length of all these certificates is supposed to be polynomial in the length of x. So if k were just 1, then you won't have any of this, and then this class sigma k would just be NP. So sigma 1 is NP. So sigma k is a vast generalization of the class NP. You would have also seen the class pi k, and it is the class of all languages such that there exists a polynomial time function P and a polynomial time deterministic Turing machine M satisfying X is in L if and only if for all y1 there exists y2 for all y3 up to qk yk, so that M of x1 y1 to yk is equal to 1. And here over here qk is either for all or there exists depending on whether k is odd or even. And again the size of all these certificates is supposed to be polynomially bounded by the size of x. So if you compare this class pi k and sigma k, then the difference was that over here the first quantifier is there exists, and over here the first quantifier is for all. Now it might seem that okay, this is a trivial difference, but as we'll see later, the order of quantifiers actually matters. Yeah, that is one of the problems. Yeah, so also again, if k were just 1, then this entire part won't be there, and you would just have for all y1 m of y1 is equal to 1, which is exactly the class co-NP. So pi 1 is co-NP. So again, pi k is a generalization of the class co-NP. Now it would have also been covered in class that if L is in sigma k, if and only if its complement is in pi k. The analog of this for k is equal to 1, that is for NP and co-NP, is that L is in NP if and only if L complement is in co-NP, right? And yeah.
Excuse me. Yeah, I don't understand that length polynomial in size of x. Can you give me example of that? I have never seen an example of that.
Okay, of a string whose length is polynomial in size of x?
Yes.
Okay, so for example, okay, where is my, yeah. So okay, let's suppose that x is a string of, okay, so let me suppose that x is in this set, okay. N is some number, so and x is an n-bit string, okay. Then here's an example of a string whose size is polynomial in size of x, okay. It's just this, x concatenated with x. So what is the size of this string? The size of this string is 2n, right?
Yeah.
And 2n is polynomially bounded by n, right?
Yeah.
So in general, px would be some function that is like this, n to the c for some c in the set of natural numbers. So for example, if the size of x is n, the size of all these strings can be as large as say n square or n cube or anything like that.
Oh.
Yeah.
Thank you.
Yes. So yeah, you were here, right? Yeah. So we saw this, and it would have also been covered in class that the class sigma k is contained in the class in the intersection of the classes sigma k plus 1 and pi k plus 1, and similarly the class pi k is also contained in the intersection of these two classes. Yeah, and finally you would have seen the complexity class ph, or the polynomial hierarchy, which is a sort of a collection of which is a sort of union of infinite classes. So the polynomial hierarchy is defined like this. It is a union over k greater than equals to 1 of sigma k, which is also the same as a union of k greater than equals to 1 pi k. Yeah, so over here I have defined ph in these two different ways, right? And I am claiming that these two are the same. So can someone tell me why this is the case? Okay, so it's because of these two things over here. So let me write. So union k greater than equals to 1 pi k is contained in union k greater than equals to 2 sigma k, right? Because of this thing over here. And now this is contained in k greater than equals to 1 sigma k. So this set, we have shown that this set is contained in this set. So we have shown this. Similarly, using the exact same argument, you can show that this is also true, and that would mean that these two are the same. And so we can define pH in like this, both these ways. Okay, so that was all for the recap. Now let's consider, let's look at some problems. Okay, the first problem is the following. Consider a CNF that is a conjunctive normal form formula phi, where every variable appears only as a negative literal. That is, in each clause That is, each clause is of the form xi1 complement or xi2 complement or and so on up to xik complement. Now consider the problem of deciding if such a formula is satisfiable or not. What can we say about this problem? So there are four options. The problem is in P. It is NP complete. It is co-NP complete, and that the given information is not enough to decide whether the problem is in P, it's NP complete or co-NP complete. So would anyone of you would like to guess what the answer is? Or does anyone of you know the answer? Okay, so the answer is this problem is in P. Okay, and the reason is very simple. Look at every clause. Every little appearing in it is negated, right? So that the only way that a clause is satisfied. Okay, so the way to satisfy a clause or a way to satisfy each and every clause is by just setting every variable to 0. Here I am using 0 to denote false. Okay, so if I, for example, in this clause, if I set every variable to 0, what do I get? It is an OR of 1s, right? So every clause would become an OR of 1s, and OR of 1s is just 1. So the entire formula would be just an AND of 1s, which is 1, right? So this very simple algorithm of just setting every variable to 0 solves this problem. Someone is, yeah. I let someone in the meet. Yeah. Yeah. So is this clear why this algorithm satisfies this formula?
Yeah.
Okay. Yeah. So then we can move on to the next problem. I can't do it. Okay. Yeah. So the second problem is, consider the problem or consider the language A such that G is a directed graph and has no Hamiltonian path. And which of the following statements is true? There are four statements. A is in NP, A is NP complete, A is in co-NP, and A is co-NP complete. Okay, so can anyone of you tell me which of these are correct, or would you like to guess?
So I think that the option number C and the option D both are correct because there exists Hamiltonian cycle is there in the NP. So its complement because its complement is there in NP. So therefore the
Right.
problem itself is in co-NP, and probably all those problems which are there in co-NP can be reduced into this problem. So therefore this is co-NP complete
Right.
also.
Yes. Yeah. So the answer is this is both in co-NP and co-NP complete, and the reason is what essentially was saying. So okay, what is, but yeah, there is just a slight technical issue. So what is A complement? It is the set of all G, so that G is not a directed graph, or it is a directed graph and has no Hamiltonian path, right? So this is the exact complement of this, right? Because over here there are two clauses. G is a directed graph and has no Hamiltonian path, right? So if I want to negate this statement, it would be G does not have G is not a directed graph, or G has a Hamiltonian path, right? Now, okay, so are you convinced that this is the complement of the language A?
Yes.
Right. Yeah. So okay, now this looks very similar to the Hempath. Oh, sorry. This looks very similar to the Hempath language. So if this weren't there, then this is just the Hempath language, right? The Hamiltonian path language.
Yes, but then what does it mean that G is not a directed graph?
Right.
So,
Yeah. Okay. So how would you be given G? G is the input. It would be given as a string, right? And from that string, you would have to decode the graph. For example, one way to give a graph as a string is to just give its adjacency matrix, right? Another way is to just give its adjacency list, right?
yes.
Right. So basically, in fact, G won't be a graph; it would be a string, right? Which represents a graph, right? So now there are strings which don't represent any graph. For example, let's say we are working with adjacency matrix representation for simplicity, right? Then now you know that the adjacency matrix of a graph has to be its size has to be like a perfect square, right?
Mm-hmm.
Because it's a matrix. So if a graph has n vertices, the adjacency matrix has to be of size n square, right?
Correct.
So any string which is not of size n square is not cannot represent a graph, right?
Mm-hmm.
So that string would fall in this category, right? G is not a directed graph.
So if it is not a perfect square, then how will it belong to how will it belong to NP then?
Okay, yeah, so that's very easy, right? Because okay, so given a string, it is very easy to check whether it represents a graph or not, right?
True, true.
Right, because all you have to do is write down that string as an adjacency matrix and check if it's a valid adjacency matrix, right?
Correct, correct.
So that is
I
in
understand.
yeah. So basically, all you need to do is just like use this pre-processing, nothing else,
Yes.
right? And because of this reason, a complement is in NP. Yeah, because given G, you just first check if it's a directed graph or not. If it is not a directed graph, you directly accept it. And if it is a directed graph, then you look at a certificate, right?
Yes.
Right. So A complement is in NP, and because of this reason, A has to be in co-NP, right? Yeah. And okay, so uh, in the class you would have seen a reduction from I think 3 set to Hamiltonian path. And while this language is not exactly the Hamiltonian path language, that almost that exact same reduction also works for this language. Okay.
So I have a query here
Right.
that if x can be reduced to y,
Hmm.
x can be polynomially reduced to y,
Right.
then does it mean that the complement of x can be polynomially reduced to the complement of y?
Right. Yeah.
Will
So that's a
will it always hold true
yeah,
or?
that will always hold true. So yeah, I can quickly explain why. Okay, so suppose you have a problem A which polynomially reduces to problem B, right? So what does
Mhm.
this mean? This means there exists a polytime computable function f such that uh, x is in A if and only if f of x is in B, right?
Correct.
Okay, so what does this mean? This also means that x not in A if and only if f of x not in B.
Hmm.
Why? Because this is if and only if, right?
Yes.
Right. And okay, what is this? What does this mean? X not in A. If x is not in A, it is an A complement, right?
Hmm.
So the exact same function f works.
So my query here is that if x is not the element of A, so does this mean that x is the element of the complement of A? Because it is not necessary that I mean the you have A or the complement of A. You can have some other, say B also, or say C
No, no,
also, or
okay,
D.
okay, okay, okay. So the universal set over here is this, right? Sigma star.
Yes.
Okay, and okay, how is A complement defined?
Yes. So do we define this complement of A as the Lehm closure of sigma minus A or some? I mean,
Okay, okay, so for in general, how do you define the complement of a set?
okay.
The
So
set minus
yeah.
the universal set minus the set, right?
Yes.
Yeah,
Yes.
so this is how A complement is defined.
Mhm,
And okay, and that is why we needed this thing over here, right?
mhm.
Because okay, so suppose we did not have this over here, right? Then what would have happened is every string which is not of size whose length is not a perfect square would have neither been A nor been A complement, right?
Mm.
And in that case, what you were saying would have been true, right? You would have defined A complement in such a way that A and A complement do not. Oh, sorry, there is a typo over here. This is A. Yeah. So in that case, we would have defined A complement so that A and A complement together do not give you sigma star, right?
Yes.
Right. So yeah, that is why yeah we defined A complement like this.
Yeah, it's clear. It's
Yeah.
clear.
And yeah, so as I was saying, yeah. Uh, so yeah, we saw that A is in co-NP, then like even though A complement is not the Hamiltonian path language, it's very close to that. And in fact, the reduction that was shown in the class would also work for this language A complement. You can try this on your own, and if you can't figure out, just ask a question in the forum or ask me in the next session. I'll describe the reduction. Okay. So A complement is also NP complete, and that would imply that A is co-NP complete, right?
Yes.
Because if every language, if every NP language reduces to A, that language's complement would reduce to A because of this, and that would be in co-NP, right?
Mhm.
Yeah. So if this is fine, we can move to the next problem.
Yes, it's
Yeah. Okay. So the third problem is consider. Yeah.
I have a question on the previous one. So,
Right.
so is there a general guiding principle in how do you get a complement of a particular language? So, for example, in this case, A was a, if you go back to the previous slide, it was a
Right.
language where G is a directed graph and has no Hamiltonian path. Like, so we did a complement of A star, and that seems to make sense. But is there a procedure or a framework on how to do it for a general language?
Okay.
In,
So
yes, please.
okay. So for a general language, A complement would just be this. Okay. However, if you do if you don't have such a nice description of the language A, then it would be difficult to give a nice description of the language A complement, right?
Right.
Yeah. So if you have a nice description of A, then almost always you can come up with a nice description of A complement.
And that would be to convert and to a or and negate the
Okay,
operands.
that depends on how you are given this thing over here, right?
Okay.
So how you are given a description of A, but you are right. If you are if A is described in such a way, then you can always just do a negation of this, right?
Okay, got it.
Yeah. Yeah. So the third problem is, so this is sort of a theoretical problem. Yeah, there is not much to explain over here. So consider the proof of the Cook-Levin theorem that was described in the lecture videos. So which of the following is correct, and select all the correct options. The first option is every row of the computational table represents a configuration. Every column of the computation table represents a configuration. Each 2 cross 3 window of the computation table represents a configuration, and every 3 cross 3 window of the computation table represents a configuration. So would anyone of you like to answer this question?
so I think that the answer should be A here because
Okay.
every row is a configuration.
Right.
And however, in the proof, we were interested in sliding the window of the size 2
Right.
cross 3 because computation is a very, very localized thing, as sir mentioned in the
Right.
lectures.
Yes. In fact, Cook-Levin theorem crucially uses that property of
Yeah,
computation. Right.
yeah.
Yeah. So the answer is each row of the computational table represents the configuration. And okay, so what does each column of a computational table represent?
So each column would be representing the transition of that particular ingredient of the configuration during the entire
Right.
process.
Exactly. So for example, if the column I'm looking at is the column of, let's say, the third cell of the read of the tape, then it would the column would the third column would basically be the third tape throughout the computation, right? Sorry, the third cell throughout the computation,
Yes.
right? So basically, the computational table gives you all the information you need about the computation. Yeah. So the fourth problem is, suppose a language B is not in NP, then which of the following has to be true? Here, has to be is important. So there are 4 options. B is in P, B is in co-NP, B is in sigma 2, and none of the above. So would anyone if you like to answer this?
So I think that the answer is D here because if B is not in NP, then quite possible that B could be an element of NP raised to the power, NP raised to the power, NP raised to the power, NP, and then so on. So it
Right.
may go quite high in the hierarchy, and therefore, you
Yeah.
can't predict anything.
Right. Yeah. So yeah, the answer is none of these. And one very simple way to do it is the following. Okay. So yeah. So every language, oh, I cleared these up. Yeah. So every language is in NP is contained in the set of recursive languages, right?
Yes.
Okay. So if some language is not a recursive language, it can't be in NP, right? So just consider the halting problem. Halting problem is not in NP, but it's not in P, not in co-NP, not in sigma 2, because all of these are subsets of recursive languages. Halting problem is not even recursive, right?
Yes.
Yeah, so this is a very easy way to see that none of these is true. Yeah.
So from here, can we infer anything about the NP hardness, wherein the problem need not to be the element of NP? So that is what I asked you in the previous session, that
Right.
NP complete are the hardest ones in
Hmm.
NP,
Right.
but NP hard could be even harder than NP complete, because if the problem itself is not there in NP, so as you can see that if the problem is not there in NP,
Hmm.
it is neither in P nor in co-NP nor in even sigma 2.
Oh no, no,
So
it need so okay. That's not true, right? Because there can exist problem there. In fact, there do exist problems in sigma 2 which are not in NP.
I could not hear you this
Oh, okay.
properly this
So
time.
yeah. So what I'm saying is there do exist problems in sigma 2 which are not
Mhm.
in NP, right?
There exists problem in sigma 2 which are not there in NP. Yes, yes,
Right.
there
Yeah.
are.
So just because something is not in NP does not mean that it is not also it is also not in sigma 2, right? That depends on the
But then
exact
it could be
language.
higher. Quite possible that the problem
Right.
we are looking for could be there in sigma 3 or could be there in sigma 4 or
Right. Yes.
in hierarchy.
Yeah.
So therefore, the NP hard problems could be harder than NP complete problems.
Right. So every NP hard problem would be at least as hard as every problem in NP, but it can possibly be harder depending on the exact problem.
Yes, yes.
For example, 3 set is NP hard, right?
Three set is NP
Yeah,
complete because the
but
problem
it is
itself
also
is
NP
elementary.
hard, right? Because
Uh,
NP complete is
so
just
it
intersection of
is
NP and NP hard.
yes,
Yeah. So
yes.
basically we have this, right? Uh, NP, uh, NP hard, and these are all NP complete problems, right?
Yes, true.
Right. So what you can say is that every problem over here or every problem over here is at least as hard as every problem over here. But there certainly do exist some problems over here which are much harder than every problem in this circle. Halt is one such problem. Then any problem, any sigma 2 complete problem would also be one such problem.
Can you repeat this
Oh
statement,
yeah.
please?
So the last thing I said that there, however, there certainly do exist. Yeah. So let me use another color. There certainly do exist some languages which are NP hard and
Mhm.
are harder than all languages in NP. For
Yes,
example,
yes.
Halt is one such language.
Mhm.
Another is any language which is sigma 2 complete.
Okay.
Because if some language is sigma 2 complete, it would be NP hard. And in sort of an intuitive way to see it is that, well, NP is contained in sigma 2. And every language in sigma 2 reduces to that language, right?
Mhm.
So every language in NP has to reduce to that language.
Mhm.
So yeah, so for example, any let's say a sigma 2 complete language would certainly be harder than every language in NP, provided sigma 2 and NP are not the same, which is an open problem.
Yeah.
Yeah.
Because sigma 2 is viewed as NP problem along with NP as an oracle. Is
Right.
this?
Yes, that's one way of defining it. Another way is, yeah, that uh, there exists y1 for all y2 during machine except m x y1 y2 if and only if x is in the language.
Yes, yes. I
Right.
understood.
Yeah.
Thank you.
Yeah. So if this is fine, we can move to the next problem. So the next problem is, suppose a language B is not in NP, then which of the following has to be false? B is in P, B is in co-NP, B is in sigma 2, or and none of these. Okay, so this is sort of the complement of the previous question over there, which has to be true. Here it's which has to be false. So which of these options has to be false? Okay, B is not in
So
NP.
B is not in NP, then
Can B be in P?
so if B is not in NP, then P cannot be in. I mean, the first option is not true because P is
Right,
there inside the NP,
right. So the first option is definitely false, right?
and B is the element of co-NP. If B is not there in the NP, then does it mean that the complement of B would be there in NP?
No, no, no. So
How
that
can I be?
that would just mean, so if B is not in NP, this would imply that B complement is not in co-NP. So B not in NP does not tell us anything about B being or in co-NP, right?
So B is not. I mean, this is slightly difficult to digest,
Right. Okay.
but
So this is written
B is not
B.
in NP. So does this mean that the complement of B is there in co-NP? Not
Okay.
necessary.
No, no, no. So if B is not in NP, then complement of B cannot be in co-NP.
Cannot be in
Right.
co-NP.
This.
Yes.
Yeah. Because otherwise, the complement of B would be in NP, which is just B, right?
Yes. Yes. Correct. Correct.
Right.
Correct. Yeah. True.
Right. So all this tells us is that B complement is not in co-NP, right? But it does not tell us anything about whether B is in co-NP or not, right?
Hmm. So B is the element of sigma 2 then?
That is possible. It may or may not be, right? Because it can also be in sigma 3, right?
Yes. Yes.
Right.
Yes.
So
None of these is the answer, I think.
no, no. So the answer is the first thing, right? Which has to be false,
Acha, false. Yeah.
right? Yeah. So the earlier question was which has to be true. This question is which has to
Mhm.
be false. It's B in P,
Yes.
right? Because P is contained in NP,
Yes.
right?
Right.
So the next question is which of the following statements is currently known to be true? And select all the correct choices. Okay, so there are four options. NP is contained in co-NP. Co-NP is contained in NP. P is contained in the intersection of NP and co-NP. And NP is contained in co-NP, which is contained in P. So would anyone, if you like to guess, or does anyone know the answer?
So I think answer number C is definitely correct.
Right.
And I'll have to look
Yeah.
into the other possibilities, and the other possibilities do not seem to be true.
Right. Yeah, that is true. Okay. So the answer is C. Okay. So first of all, yeah. So what we'll do is we'll see that why these three possibilities don't seem to be correct. Okay. At least according to current knowledge. Okay. So the first thing that we'll prove is this: if NP is contained in co-NP, then NP. Okay. So NP is contained in co-NP if and only if NP equals to co-NP. Okay. This is the first thing that we'll prove. Now, this would immediately imply that we don't know that this is true. Why? Because if this were true, if we know that this is true, then we would have known that NP is equal to co-NP, right? But that proving that NP equals to co-NP or that NP not equals to co-NP is an open problem, right?
Yes.
So proving this claim would mean that the first option is not known to be true, right? Is this fine?
Yes. Yes.
Yeah.
Yes.
Okay, so let's prove this. Okay, so the one direction is clear, right? So first we'll prove, yeah. So just a second, someone wants to enter the meeting. Oh yeah, someone joined. Yeah. Okay, so yeah, first we'll prove this direction that NP equals to co-NP implies NP is contained in co-NP. This is trivial, right?
Yes.
Right, because every set is a subset of itself.
Yes.
So the harder direction is this one. So let's do that. So suppose NP is contained in co-NP. Then let us fix any language L in co-NP. Now by the definition of co-NP, L complement has to be in NP.
Mhm.
Now, oh yeah, there is a type over here. This should be, Wait, no. Yeah, so fix any L in co-NP. So its complement has to be in NP. Okay, right. Now, what do we know? We know that NP is contained in co-NP. That was our assumption, right? So that would mean that L complement is also contained in co-NP because it's contained in NP, right?
So it's not that clear that if NP is contained in co-NP, then we fix any L, which is
Right,
element of co-NP, its
right.
complement would be there in NP. So hence the complement of L is the element of
Co-NP.
co-NP.
Okay, right. So L bar is in NP, right?
Mm-hmm.
And NP is a subset of co-NP.
Mm-hmm.
So this, what does this statement mean? This just means that for all A in NP,
Mm-hmm.
A is also contained in co-NP, right?
Mm-hmm.
So if over here our A is just L complement,
Mm-hmm.
so L complement also has to be in co-NP because it's in
Mm-hmm.
NP.
So for all A which is there in NP, it should be there in co-NP as well.
Because of this assumption, right?
Mm-hmm. But this implies that L is the element of NP.
Right.
Is this true?
So this
Correct.
implies that L is an element of NP,
Mm-hmm.
and now this is true for we did not fix any like L was any arbitrary language in co-NP, right?
Mm-hmm.
And so this means that every language in co-NP. So for every L in co-NP, L is also in NP, which means co-NP is a subset of NP, right?
Mm-hmm.
So NP
Yes,
is
so
equal to co-NP, right?
yes. We reached
So
to the same
right. So
conclusion.
basically this implies that these two are equivalent, right? So
Mm-hmm.
now we know that proving whether NP is equal to co-NP or NP is not equal to co-NP is an open problem.
Mm-hmm.
So uh, which means that the first option is not known to be true, right?
Mm-hmm.
Yeah. Then the second claim is sort of analogous. Second claim says that co-NP contained in NP if and only if NP is equal to co-NP.
Mm-hmm.
So yeah, over here we have just like reversed these two. And the
Yes.
proof is exactly the same, so I won't cover it. You can try it on your own. If you have any
Mm-hmm.
doubts, you can ask me in the next lecture or on the forum. Okay. So thus options A and B are the same as NP equals to co-NP, and therefore they are not known to be true. Now
Yes.
let's look at option D. Option D is NP is contained in co-NP, which is contained in P. But this means that NP is contained in P.
Mm-hmm.
That would mean NP equals P, right?
So which cannot be true, so therefore.
Well, okay, most people believe it's not true, but we still don't know for sure, right?
We do not know. We do
Right.
not know.
Yeah, so we do
We don't
not,
know
yeah,
the
we do not know whether this is true or not, right? So this is also not, so this is also not known to be true. So we have
Mhm.
eliminated A, B, and D, and C was covered in class, right? I think,
Yes,
right?
yes.
So yeah, if this is fine, we'll move on to the next problem. And here is, so at the beginning of the class, I was mentioning that the difference between sigma k and pi k might look like trivial. It's just that the order of quantifiers is changed, but that actually matters. So let's see an example of that. Okay. So consider the following two statements where x and y are from the set of positive integers. So x and y are 1, 2, 3, 4, so on, right? The first statement is statement P. For all x, there exists y such that y is greater than x. The second statement is Q. There exists y for all x such that y is greater than x. And we are supposed to select the correct option. The options are P is correct, only P is correct, only Q is correct, both P and Q are correct, and none of the statements are correct. Should be is correct. So, which of the would someone of you like to guess the answer, or do you know the answer?
So on the part A is correct. Only E is
Right.
correct.
Yeah, that's the answer. Yes, only P is correct, and yeah. So let's see why that's the case. Okay. So statement P is for all x there exists y so that y is greater than x. So this statement is saying is the following. For every integer x there exists an integer which is greater than it, right? So is this fine?
Yes.
Okay, so all we have to do is fix an integer x, create an integer y which is greater than x, right? Well, just pick y equals x plus 1. Then y is greater than x, and so is p is true, right? So is this fine?
Yes.
Right. Now let us look at statement q. It says there exists y for all x such that y is strictly greater than x, right? So now what is this statement saying? There exists a universal y which is greater than all the integers, right?
So there exists a y, and there exists a y only. Y universal y. There exists a
Okay,
y.
no, no, so okay, what is this saying? There exists y for all x, right? So
Yes.
what this is saying is there exists y such that y is greater than 1, y is greater than 2, y is greater than 3, y is greater than n, and so on, right? So there exists a common y, right?
So what is the domain of x and y here?
So yeah, that is given over here, where x and y are from the set of positive integers.
Yes. So yes. So therefore, it cannot be correct.
Right,
Following, I know one principle, the principle of well ordering.
right,
So because of that, yeah.
yeah. So basically, no integer can be greater than all the integers, right?
Mhm.
Here's a very simple way of proving it. Pick any integer of y, okay.
Mhm.
Fix y and let x be y. Y is not greater than itself, right?
Mhm.
So this statement would be false.
Correct.
So the difference between the two statements is the following. The first statement is saying, so both statements are saying that there exists some y, okay. But what the first statement is saying is the following. For every x, y can be different, right? But what the second statement is saying is that there exists a common y for all x. So is the difference between the two statements clear?
Yes, yes. It
Yeah,
was even clear during the class also.
right.
Two examples for it. Sort
Okay,
of two examples.
okay, right. Yeah, so in that case, we can move on to the next problem. Yeah, so the
Uh,
problem,
Excuse me, sir, on the previous
right,
slide. So, I mean, it is also possible to read that as there exists y for all x. I mean, read that as there exists a y for each x. Uh, I mean, that also seems to be an acceptable interpretation of that statement, right? Like,
which statement? The
I mean,
second
so
statement?
there,
This one?
yeah, so there exists y for
Right,
all x. So it's, I mean, it makes sense when you say it's a global y for all the possible values of x, but it
right,
also makes sense to sort of read it as there exists a y for each x.
okay.
Uh, and then you can say y equal to x plus 1, and then that statement becomes true, right?
Okay, so what does this mean? There exists y for all x.
Okay, like you can't replace for all by for each. That will be changing the statement, right?
Right.
Okay.
Yeah, and so what you are saying is basically, okay, so what you are what you want to do is, so over here what you are doing is you are fixing a y and then worrying about x, right?
Hmm.
Over here you are fixing an x and then worrying about y. That is why you can keep on changing your y.
Okay.
Yeah,
Okay. Thanks.
yeah. So the next problem is a Boolean formula phi is said to be the disjunctive normal form DNF if phi is C1 or C2 or up to Cm, that is, it is an OR of clauses, okay, where each clause is an AND of literal. So for example, Cj looks something like xi1 or xi2 complement or up to so on xik, okay. So is a formula in the disjunctive normal form clear?
Yeah, so this is the disjunction of the conjunctions, is it?
Right, yeah. So in the class you would have seen the conjunction of disjunctions. This is the
Mhm.
opposite of that.
Hmm.
So that
So
in the class
so
you would
so
have, right.
so when this y when this phi turns out to be true, when each of C1 C2 is true or what? No.
Okay, so
Yes.
yeah,
Either of
yeah, right.
C1 or Cm is true.
Right, so that's the question. Basically, that's the question.
Okay,
So
okay.
consider the problem of deciding if such a formula is satisfiable or not. So what can we say about this problem? The options are the problem is in P, the problem is NP complete, the problem is co-NP complete, and the given information is not enough to say which of these three things is true. Yeah, so now using what you were saying, you can answer this question.
Okay. So yeah. Uh, mhm.
Okay, so what were you saying? That phi is satisfiable if any of the clauses is satisfiable, right?
Yes. So any clause itself could be a Boolean formula. Is this so?
Right, so any clause itself looks like this.
Yes.
It's
So
an or
any
of
clause,
literal, end of literals.
end of literal. So every clause in itself is in the form of CNF. Is so?
No, 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 no. It's okay. It's a CNF, but it's a trivial CNF because
It is a trivial.
everything over here is just one literal, right?
Yes, but still, say if every clause comprises of the n number of the literals, then
Hmm.
still there would be 2 raised to the power n number of the possibilities to be explored to show
Right.
the truthfulness of an individual clause here.
Why? So okay, you don't need to show that this clause is a tautology, right? You only need to show that this clause is satisfiable.
Satisfiable. So if any clause is satisfiable, the
Hmm.
formula
Right.
will become satisfiable.
Okay. So
Right?
yeah, let me skip a slide and go to the immediately next slide. Okay. Yeah. So we are skipping the answer directly go to the solution. Okay. Yeah, because we are very close to the answer solution. So a satisfying assignment for any clause is also a satisfying assignment for a formula, right? That is what we have concluded so far, right?
Mhm.
Right. So which means that phi is satisfiable if and only if there exists an I, so that Ci is satisfiable,
Mhm.
right? This is what we've agreed on up to now. Okay,
Yes. So
right,
CI is not a contradiction.
right. And okay, when can Ci be a contradiction? Ci is a very simple clause, right? It looks like this. It looks something like this: xi1 and xi2 complement and so on up to say xik. So when can something like this be a contradiction?
So, I mean, this could be a contradiction when xi1 and you find we find the xi1 and its complement at the
Right,
same place.
right. So yeah, because if xi1 and x, so if okay, first of all, if xi1 and xi complement occur together over here, that is
Mhm.
saying that xi is both 0 and 1, which is not possible. So this is called clearly a contradiction, right?
Mm.
Now suppose you don't have something like this, okay? So suppose that all of these I1, I2 and Ik are distinct,
Mhm.
then the clause is satisfiable. Why? If a literal appears as it is, set it to 1. So we will set x1 to 1, xi2 to 0, xik to 1 and so on, right?
Mm.
This would clearly satisfy the clause, right?
Yes.
And we can do this because xi1 does not appear negated as well, right?
Mhm.
So basically the clause is satisfiable if and only if all of these are distinct, right?
Mm. Mhm.
Yeah, so basically what we have argued so far is this: phi is satisfiable if and only if there exists a clause which is satisfiable, and it is easy to check whether a clause is satisfiable or not. Why? Just look at it.
No, no, no. I don't think that it is easy to show that a clause is satisfiable because even if all the clauses are all the literals are distinct, quite
Hmm.
possible that we might be having a large number of the literals, say 20n number of the literals, and out of the 20n number of the literals, say n number of the literals are all distinct, right? But to ensure this thing that none of the literal is appearing uh, as a complement of itself in the Boolean formula.
No, no, not in the
Uh,
formula, just in this one clause, right?
yes, even in the one clause, I
Okay,
mean,
so
so
the clause looks like this, right?
is
xi1.
there any is there any fixed format of the clause given in the question? Because
Yeah,
I could
yeah.
not see the
Okay,
question
so
completely.
yeah, so this is a format of a clause, right? Cj is xi1 and xi. Okay, so over here it's where each clause is an end of literals, right? So here is an example of a clause. Every
So
way,
we can have we can have a different form of the clause also,
yeah. So right,
wherein the
something like
wherein
this
the
can
second
also be
second
true.
literal need not to be complemented.
Yeah, that is all. Okay, yeah, that is all. That's also fine. But every clause is an end of literals, right?
Mhm.
So we have this. Every yeah, where is this? Where each clause is an end of literals. Okay, and what is a literal? A literal is either this or this, right?
Mhm.
So what does this statement say? Cj looks like this: y1 and y2 and up to yk, where yi is either xi 1 yeah, or xi complement, right?
No, no, it's not necessary.
Okay, what is a literal? So okay, every clause is an end of literals, right?
Yes,
So every clause is y1 and y2 and y up to yk, which where y1 is a literal, y2 is a literal, yk is a literal, right?
yes.
Okay, now what is a literal?
So literal could be a single literal, or it could be the its complement,
Right, so a
or
literal could be a variable or its complement, right?
yes.
Okay, so that is exactly what I've written over here, right? Yi is either xi or xi complement, right?
Mhm.
So Cj looks something like this, right? Not necessarily in this form. You are right. Xi2 can appear as xi2, but something can also appear as a complement, right? So basically, each and every element of Cj is either a variable or its complement, right?
Mhm.
That is fine.
But what if all the literals are distinct? My only apprehension here is that if we want to show the truthfulness of a clause, then how
Hmm.
many possibilities do we need to explore
Okay, no, no,
if
no,
we
no.
do
Okay,
not take this heuristic into the
okay.
consideration?
Forget about the heuristic. You are given a clause where
Yes.
every element is either a variable or its complement. Okay, and
Yes.
you only want to find, you only want to say that it is satisfiable or not, right?
Yes.
Okay, so what do you need to do to show that it is satisfiable or not? Just
Yes.
produce
So
a
so
satisfying assignment, right?
yes. So but then we have distinct literals here ranging from x1, x2, and say till
Right,
xk.
right. But okay, you are given this formula, right, as an input. So
Mhm.
this number cannot be, this number is polynomial in the size, right? This number cannot be more than the size of the formula.
Having only two possibilities, either 0 or 1.
No, no, no. I am talking about this number, ik. Ik is a number of literals in this clause, right? Now suppose ik is polynomial in input size, then we are fine, right?
So does this mean that we do have only one literal xi, and this xi1 represents its position of the xi literal? Then probably it can be solved in the polynomial time.
No, no,
If
so,
we have been given only one literal, say only xi is allowed while defining cj.
no, 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 no. That we don't need anything like that, right? Okay, so Cj looks something like this, right?
So can we write, say, what is c2 then? Let us write c2.
Okay,
So c2 could be,
right. C2 could be exactly in this form.
so what c2 here is then xi1,
Okay,
uh, or
and
n
and
xi2, and
xi2.
xi2 its complement, and then uh,
Okay.
and say xi3 and its complement, quite possible
Oh
if
wait,
we.
xi3 and its complement. Is this what you are saying?
No, only xi3 complement. Is
Uh,
this a possibility?
yeah, this is possible because xi3 complement is also a literal, right?
Yes.
Okay.
So now for xi1, my question is pretty
Hmm.
actually straightforward. My only query is that we can have two possibilities for the xi1,
Right,
and
that is
similarly
true.
two possibilities for the xi2,
Right.
and so there would be 2 raised to the power n number of the possibilities to be explored, because this is end.
No, no, no,
So
no. Okay, so you are right. There are 2 to the n possibilities, but we don't need to explore all of them. Because what is our goal?
why why
What is
why
our,
why
what is our goal?
our goal is to show that it becomes true. C2 becomes say true,
Okay. So
right?
suppose magically I could come up with an assignment which makes C2 true. Then I would be fine, right?
Yes.
Okay. Now there is no need for magic over here because of the following reason. I would okay. Start looking at C2. Okay.
Hmm.
The first thing you would see is xi1.
Yes.
Now it does not have a complement on top of it, right?
Yes.
So make it 1. The
Yes.
next thing you would see is xi2 complement.
Yes.
It has a complement on top of it, make it 0, and so on. Okay.
Yes.
Now this thing would clearly satisfy C2. Just
Yeah,
C2.
correct. Because probably in that case, we need not to explore 2 raised to the power
Right.
n possibilities because we are very much sure that wherever we find a complement, we need to mark its value as 0 only.
Right.
Is this so? But it
Yes.
is not necessary. It is not necessary.
No, no, so this is not necessary. Oh wait, actually this is necessary if you want to make this clause true, right? Because if you make xi2 1, then this clause
Huh.
is false, right? So that this
Yes,
clause is
correct.
exactly what. So there are 2 to the n possible assignments, out of which only one is correct,
Yes, correct, correct,
right?
correct. So there would be polynomially large number of, I mean, we need not to explore the exponentially large number of
Right,
the possibilities. Number of possibilities would be polynomial. Yeah, very, very interesting question.
right,
And yes, therefore this problem is in P,
right.
definitely.
So all we need to do is number 1. So all we need to do is the following, right? For all I in M, does someone want to? Uh, oh yeah. So Darshan, in all the problems, the language is implicit. Okay, the alphabet set is implicitly 0, comma 1. Is that what you are asking? Because language being 0,
Yes,
comma
sir.
1 does not make sense,
Yep.
right?
So the M in the
Yeah,
alphabet is 0.
right, yeah. Yeah, but that we can assume without loss of generality, right? Because using 0, comma 1 you can encode everything efficiently.
Yep, yep.
Yeah. Okay, so all we need to do is find if there exists a clause which is not a contradiction, right? That is very simple. Just go over all the clauses, check if it is a contradiction or not using this simple procedure over here, and if there exists a clause which is not a contradiction, phi satisfiable, otherwise it is not satisfiable, right? So is everyone
Yes.
convinced that this is in P?
Yeah, I'm convinced that.
Right. Yeah, so okay, yeah, that's the answer. And so the only thing that we changed was, so D and F satisfiability is in P, but C and F satisfiability is NP complete, right?
Yes.
Right, yeah. So yeah, the form of the formula does matter. Yeah. So the next problem is, suppose P is not equal to NP. Then which of the following statements about the polynomial hierarchy or PH can be inferred? The options are PH collapses to NP, PH collapses to sigma 2, PH collapses to pi 2, PH does not collapse to any finite level, and none of the statements can be inferred. So does anyone know the answer, or would you like to guess it?
I don't know the answer, neither I know the logic, but
Okay.
my intuition says that probably the answer D is correct, that it will not collapse at any level if P is not equals to NP.
Mm, okay. That is what that is what you would believe, right? Because okay, if P does not equal to NP, why should any higher class be equal to? So yeah, what you are basically saying is this, right? If P not equals to NP, why should sigma k be equals to pi k for some k, right?
Yes.
Yeah, so intuitively it feels like this, right?
Yes.
But the question is, can we get so this? Okay, so intuitively feels like it. But the question is, can this be inferred? So the question is asking us this: if P is not equals to NP, can you for sure say that sigma k is not equals to pi k for any k? The question is, can you do this, or at least do we know how to do this right now, like with our current knowledge of computational complexity? That's what the question is asking, right?
Yes.
Right. So yeah, so let me tell you the answer is none of these, because right now, okay, P not equals to, just because P not equals to NP does not, right now we are not able to know, tell any of this, right? Now it is possible, it might be as well possible that if P not equals to NP, P does not collapse at all. But right now we don't know that, right? So right now we
Hmm.
cannot infer it, right?
Yes.
Right, yeah. So the answer is none of this can be inferred. Now let's look at sort of a complement of this question. So here we have P not equals NP. What if P
Hmm.
equals NP? So suppose P equals to NP, then which of the following statements about the polynomial hierarchy can be inferred? The options are the same. P collapses to NP, PH collapses to NP, PH collapses to sigma 2, PH collapses to pi 2, PH does not collapse to any finite level, and none of the statements can be inferred.
Yes, so if P is equal to NP, then probably the answer A would be correct, that
Right.
everything will collapse down. Will,
Yes.
yeah.
So I think, was this covered in class?
Yes, yes, it was
Okay,
covered
right,
in the.
yeah.
Yeah.
Okay, now because of this, technically even these two are correct. Because the polynomial hierarchy has collapsed. So sigma 2 is equal to pi 2 is equal to NP.
Yes.
Right. Because, yes, okay.
I have a doubt here
Right.
that so is there any example of the problem which is element of sigma 3
Sig-
and which is not there in sigma 2
Okay,
and
first of all, you are asking this, right? Does there exist a language L in sigma 3 such
Mhm.
that L is not in sigma 2? But this would
So
imply
because
something that we don't know right now. This would imply that
content,
pH does not collapse,
yes,
right? Because this would mean that, okay, sorry, this would mean that this would at least mean that pH does not collapse to sigma 2, right? pH as my
yes.
pH as my pH might as well collapse to sigma 4, but right
Mhm.
now we don't even know that pH does not collapse to sigma 2, right?
We do not know it
Right. So
yet.
right now we do not have any example of any such language,
Mhm.
but it is, okay, I think a significant amount of people believe that pH does not collapse, in which case any language which is sigma 3 complete would be a good example of a language that you want.
Mhm.
Right. Yeah.
So in class, one example, maximum of the independent set was taken, and max independent set was modeled as the sigma 2 problem, because there we
Right.
require say probably two y's, because there exists one y1, and then how do we model this max independent set as sigma 2? It was discussed in the class. So how do we, I mean, what is required to model a problem as an instance of say sigma k?
Sigma
we,
k.
we, we
Okay.
start with we start with there exist, and then followed by an alternative
Right.
universal and the sigmas.
Yes. Okay. So, yeah. So what does it look like? There exists y1 for all y2. There exists
Mhm.
y3 so on. Qk yk. Qk
Mhm.
depends on, it's whether it's there exists, or follow depends on whether k is odd or not.
Mhm.
M of x y1 to yk is 1, right?
Mhm.
Now, okay. First of all, k. So this is sigma k, right? But it is perfectly fine to skip some of these quantifiers, right?
Mhm.
Like some of these quantifiers can as well be dummy, right?
Mhm.
For example, there exists y1 for all y2 m y. Oh, sorry, I forgot x. M x comma y1 comma y2 is equal to 1, right? Now, suppose I want to make y2 dummy, then what will I do? I will completely ignore, my machine will completely ignore y2.
Mhm.
Then this would be trivial to, right, for all y2 to work, if it just ignores y2 completely. So basically, if you want to model some problem as sigma k, you need to come up
Mhm.
with like at most k alternating quantifiers, starting with whether there exists quantifier.
So from where will I bring, or from where within the problem I identify that okay, these y2, y3 and settle
Okay,
yk is.
that depends on the problem. Yeah, that is highly dependent on the problem. For example, I remember one problem. It's called the VC dimension problem,
Mhm.
and it's not at all trivial to show that. So it's I think in sigma 3, but it's not at all trivial to show that. So yeah, I mean just yeah, I mean just as like finding whether a reduction exists or not is not trivial. You have to try out a lot of things. Similarly,
Mhm.
to figure out whether a language is in sigma k or pi k is also not trivial. Like it depends on the language. You have to like yeah try a lot of things out and understand the structure of the language better.
Okay,
Yeah.
and then from here, what you wrote here is after this there exists y1. Whatever remains, in fact, is pi k or pi k minus one because it starts
Right. Yeah.
with.
That is pi k minus one. Right. This entire thing is pi k minus one.
Okay, so sigma k is equal to there exists y1 and then followed by the pi k minus one.
Yeah. So a
Is
pi
this?
k minus one statement.
Could not hear you.
So
So pi k.
yeah. So the way, if you want to model this as a pi k minus one language, you would
Yeah.
also need to sort of fix y1, right? So
Yes.
now your
Yes.
language would be like, so the strings in language would be a tuples of this form, right? Because you have to fix a y1,
Yes.
right?
So for yeah.
Yeah. But yeah,
Easy.
that's a trivial, like that's a yeah, that's a I think a trivial modification. I think this was done in class, right? To
I do
show
not remember. Probably sir might have explained this or might have
yeah.
I
Okay,
might
so
have
he
skipped
might
it,
have
but
so was this shown in class? No, no, not this. Pi k is contained in sigma k plus one.
it was
Right.
discussed.
Yeah. So over there you do basically exactly the same thing.
Okay.
Yeah.
Okay.
Okay. So yeah, let's
It's
look
clear.
at the next problem. So out of the following choices, select all of the choices that are definitely false as per the current understanding. Okay. So the options are sigma 2 is equal to pi 2, sigma 2 is contained in pi 2, sigma 2 and pi 2 are intersecting sets but neither of them is a subset of the other and they are disjoint sets. So as per our current understanding, which is what is definitely false? So you can list all the statements that you think are false and then we can show that the rest are not known to be false. Okay, so according to our current understanding, do we know that sigma 2 equals to pi, that sigma 2 equals to pi 2 is definitely false? Okay, so suppose sigma 2 equals to pi 2 were false, right? Then what would be true? Sigma 2 not equals to pi 2, right?
Yes.
But this would imply that pH does not collapse to sigma 2.
Which we do not know.
Right. So this is not known to be true, right? So not known to be false.
Hmm. But neither it is true.
Right. So okay, the question is select all the choices that are definitely false as per the current understanding, right?
Okay.
Yeah. Similarly, for if sigma 2 is in pi 2,
Mhm.
then again pH would collapse to the second level,
Mhm.
right? So basically, okay, we saw this, right? If NP is contained in co-NP,
Hmm.
then N okay, not this double implies NP equals to co-NP, right? This we saw, I think, a few problems back, right?
Yes. 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 Yes.
Using the
Yes.
exact same argument, you can show
Yes.
that this double implies sigma 2 equals to pi 2. There is NP is sigma 1, co-NP is sigma 2.
Hmm.
Yeah, so the exact same argument works.
Mhm.
So if yeah, so if P, so this would this is also the same as sigma 2 equals to pi 2, but this would mean that pH collapses to sigma 2, right? Again, that we don't know.
Mhm.
Okay, now what is this saying? Sigma 2 and pi 2 are intersecting sets, but neither of them is a subset of the other. So what this is saying is this: sigma 2 intersection pi 2 is not an empty set, but sigma 2 is not a subset of pi 2 and pi 2 is not a subset of sigma 2. Okay. However, if sigma 2 is not a subset of pi 2, then this thing would imply that uh, sigma 2 is not equals to pi 2. Just take the contrapositive, right?
Hmm.
But that what would that imply? That would imply that that pH does not collapse to sigma 2, right?
Neither we know this thing.
Right. So we cannot say with certainty that A is false, B or B is false or C is false, right?
Hmm.
So we are only left with D.
Sigma 2 and pi 2 are disjoint sets.
Right. But we know this, right? Sigma 2, sigma 1 and pi 1 are both subsets of sigma 2 intersection pi 2, right? This we know.
Hmm.
Now sigma 1 is just, okay, sigma 1 is NP, and we
Hmm.
know that NP is at least one problem, right? 3 set.
Hmm.
So this is not empty, right? So the intersection of sigma 2 and pi 2 is not empty. So they are not disjoint sets, right?
Hmm.
So this is definitely known to be false. Yeah, and that's the answer.
Yeah.
Yeah. So I think that was it for today. If you don't have any questions, we can meet next time. Or yeah,
So,
if you have questions, you can ask them now.
yes, so I find it quite difficult to understand this polynomial hierarchy
Right.
actually.
Yeah.
So then I referred the other literature also,
Hmm.
and wherein this hierarchy is given in the form like say in a different format
Right.
altogether.
The oracle form.
Yes, in the
Right.
oracle form.
Yeah.
So how to study this polynomial hierarchy to understand the things better?
So I think, okay, one of the, so if you are confused between the definitions that were covered in class and
Hmm.
the definitions that use an oracle, the best way
Hmm.
to understand that would be to do the following. Try to prove on your own that the two definitions of sigma 2 are the same.
Hmm.
I think, yeah, if you try to do that on your own, yeah, I think you would get a very good understanding of the two, like the similarity between the two definitions.
Okay,
Yeah,
okay, okay.
and again, if you can't do it, then I think just post a question in the forum, and yeah,
Hmm.
like one of us can, like one of the TAs or the faculty can, like either point you to a reference or show you the reduction. Sorry, show you the equivalence.
Sure, sure.
Yeah,
I'll do that.
yeah, and yeah. So if
Thank you.
you,
Thank you so very
yeah,
much.
so if you don't have any other questions, on the we'll meet next week on the same time.
Right.
Yeah,
Thank you. Thank you
thank
so
you.
very much.
Yeah,
So I'm leaving the
yeah.
meeting.
Bye.
Thank you. Bye.